We'll move on to test review number 2 just to get a little bit more information in here. So we spent a good bit of the first couple weeks talking about kinetic and potential energy with things falling. And so let's remember if we do have an object that is at a height and it's not falling yet, but it has the ability to fall, that hopefully we remember that it does have potential energy. And that potential energy is based upon several things. It's based upon the mass of the object, and it's based upon the height at which it is located, and it's based upon the gravity that would be pushing it down. And on Earth, gravity on Earth we're going to say is going to be 10 meters per second squared. That's an acceleration rate that we'll talk about later this semester. So effectively, let's think about again how the math works on this, so that if we make the mass bigger, that's going to result in a greater amount of energy, and if we make the height bigger, that's going to result in a greater amount of energy. The same thing would be true with the gravity as well. So, you know, if we had two objects that were the same mass, then obviously the one that was at a greater height would have more potential energy, and if we had two objects that were at the same height, then the one that was a larger mass would have more potential energy. When we moved on to kinetic energy, something had to be moving, and so our formula for that, it still included mass, so we would need to take the size of these things into consideration. But the other thing that was important with kinetic energy was the speed, and we squared that. So again, if we had two objects that were the same size, then if they were going at different speeds, they would have different amounts of kinetic energy. And if we had two objects that were going the same speed, say this one and this one, then the mass would still play an important role in determining how much kinetic energy. Because the velocity component is squared, the velocity actually usually causes a greater change in the kinetic energy than the mass does. So these are our two formulas for that. We need to take those into consideration when we're doing our calculations. We then started discussing heat transfer, and we mentioned there was really three ways that heat could travel from one place to another. So we had conduction, we had convection, and we had radiation. Now in general, heat always travels from where something is hot to where something is cold, if you want to think of it in those terms. So overall, if we brought two objects together, what we would see is energy would move from the hot object to the cold object. Now, in reality, energy does move from the cold object back to the hot object, but let's think about this. The hot object is going to have more energy. The cold object is going to have less energy. So even though some energy is going to be leaving the cold object, it's going to be receiving more than it's giving. And it's kind of like money. You know, if someone's giving you a lot of money and you're still spending a little bit, you're eventually going to get more and more and more money. Where in the reverse is true over here with the hot. So let's if we're thinking of money equaling energy, this would be like spending. So the hot thing is spending, 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 and it's not getting very much back from it. So eventually its money is going to get less and less and less. So in reality, anytime we have two objects near one another, there is an exchange of energy in both directions. However, the object that has a higher temperature is going to have more energy. It's going to be able to have more energy that's going to be moving to eventually go to where the other one is. Okay, so when we do have heat energy move from one place to another overall, conduction, convection, and radiation, pointed out, let's try to think of three words to think about with all of these. Conduction is when we have things that are directly touching one another, such as a pan on a stove. Convection is when we have gases or liquids flowing, such as when the air is moving through the room, or water is heating up a bathtub, the magma inside the earth. So anything that's usually flowing in some kind of pattern, so that when it gets hot, it rises, and then it will start coming back down as it cools off. Okay, So there's no necessarily touching that we would have in here, we just have flowing. And then finally, radiation is going to be when energy moves through waves. And this might happen in space. In fact, this is the only one that can happen in space. The waves from the sun are able to travel through emptiness. And so these are the three main things that we have in terms of heat transfer. So if we have objects touching, conduction. If we have objects, if we have liquids or gases flowing, that might be convection. And if we have invisible energy that's in the form of waves, that's going to be our radiation. And finally, we try to make a little bit of a distinction between these two terms that usually in everyday life we don't think of as being different. And those terms are heat and temperature. They are not the same thing. They're related, but they're not the same thing. So when we discuss in physical science, when we say heat, what we're talking about is the total energy, because heat is a form of energy. When we're talking about temperature, what we're doing is we're making a measurement, and what it does is it's going to measure the average kinetic energy in a substance. Okay, so let's think about how this works, because we could have a couple of objects that we could be able to compare. So let's say I've got this large container and I've got this little tiny container. And I'm going to let the amount of kinetic energy be represented by the size of the dot. Alright, so let's say like a little tiny dot is going to equal something that has a small amount of energy, and a large dot would be a large amount of energy. So let's say I've got this little tiny amount of liquid over here, and I've got this larger amount of liquid over here. Alright, so but let's say this tiny amount of liquid has got these really big dots in it. So all the individual particles in here, and the dots aren't really representing the size of the particles. I'm just trying to use those to say that how much energy would they have. So this would be few. There's not a lot of, because it's a small amount, there's very few molecules in here. But each one of them has a large amount of kinetic energy. I don't know what just happened there. Whereas with this one, let's say we have a whole lot of it, but all the particles in here just don't have a lot of energy to them. And I guess I could keep going on and keep going on and keep going on with this. So let's say the small dots equal let's say that they're like 5 joules of energy, and let's say the large dots equal 10 joules of energy. Well, if I stuck a thermometer in here, remember thermometers they don't measure heat, thermometers measure temperature. So if we stick a thermometer in each one of these, the thermometer is going to measure the average kinetic energy. Well, the average kinetic energy in this one's actually pretty small, because remember, each one of these particles has only 5 joules of energy. So if every little particle in here only had 5 joules of energy, then my thermometer would say, well, the average is 5 joules, and that would correspond to some kind of temperature on the temperature scale. Whereas this one over here, all the dots are large. So each dot has way more energy. And so when I stick the thermometer in, again, what's it measuring? It's measuring average kinetic energy. So the thermometer would tell me that it's got 10 joules that are on here. All right, so if we just look at the temperature aspect of this, then what we end up seeing is that the smaller one over here, this is going to have a higher temperature. All right, so the temperatures of these are not the same. This one's going to have a higher temperature. But let's go back and look at the total energy. The total energy would be how much, if we added up all the energy that was in here. Remember, each one of these dots is worth 5. Each one of these dots is worth 10. And because this is a smaller amount, well, there's just not going to be near as much energy in this. So if we if we added up all this, I can see that there's 4 dots in this one. The total in this one would be 40 joules. I have no idea how many dots I put in this one, but it's a lot more than 40. So it'd be 5 times, let's say I put 50 in here. There might be 250 joules of energy in this one, because each molecule has energy. And even though there's more energy per molecule over here, there's way more molecules over here. And so if we compared the amount of total energy, then this one would actually have more total energy because there's more molecules. All right. So it would be really similar to if we wanted to compare, and I actually had a question about this on one of our assignments, if we wanted to compare the amount of energy in a glass of water versus the ocean. All right. So I might have a glass of water that was boiling. And one way that we can really think about this is what would happen if we combined them. So if I had some boiling water, a glass of boiling water, and then I had the ocean. So if we stuck a thermometer in this, hopefully we would understand that the thermometer would say, this is a higher temperature over here, because it's boiling. The ocean's not boiling. So we know that this one might be 100 degrees Celsius, whereas the ocean might only be 20 degrees Celsius. All right. But what about the total amount of heat? Which one has more heat? And again, so if you're still thinking that heat and temperature are the same thing, you would answer that wrong. Which one has more heat? Heat is total energy. All right. So the ocean would end up having more total energy simply because it is way more massive. Every little water molecule in it, even though it doesn't have as much energy compared to the boiling water, there's just way more of them. Just way more of them. And so if we combine these, let's think about what would the resulting temperature be. Like, you know, would the boiling water turn the ocean into boiling? Or if we poured the boiling water into ocean, would it even make a dent in it? No, it wouldn't. If we poured a cup of boiling water in the ocean, effectively there's going to be no effect on the ocean whatsoever. So we would say that there's more total energy in the ocean, although the cup over here might still, well, not might, the cup over here has a higher temperature, so it has more average kinetic energy.